Okay, guys, I think it's time to get started. Hello, everybody. My name is Heiko Seeberger. I'm working for CodeCentric in Germany, and I'm really glad to be here again in Zurich. Today, I want to talk to you about Akka and AngularJS in combination to build reactive apps. Before we get started, I'd like to know who of you has already used Akka? Okay, cool. I think that's 1/3 as far as I can tell from looking against the light. Awesome. AngularJS? Any users here? Okay, excellent. That's more than half. Okay, so reactive apps boils down to talking about the reactive traits as defined in the Reactive Manifesto. Has anybody read the Reactive Manifesto so far? Okay, cool. For those who haven't, please go there and just read those 20 lines, maybe 50 lines. It's 5 minutes, but worth reading, I think. But I try to describe the main traits here in a short version. In the Reactive Manifesto, they say that a system has to be responsive because that is really what makes a system useful and valuable. Responsive means that the system will respond in a timely manner under any conditions, okay? And there might be numerous conditions, very functional conditions, but there are two very important non-functional conditions which are also addressed here in the Reactive Manifesto. These are load, which boils down to elastic. So a system has to remain responsive under increasing load. So it has to be able to scale out and scale up, and also scale down if the load goes down again. And it also has to be or remain responsive in the face of failure, and that is resilient. Okay, so if part of the system breaks down, that should not lead to taking the whole system down, and the whole system should still be as responsive as possible. The Reactive Manifesto defines message-driven as one way to become responsive and elastic and resilient. And that means, message-driven means asynchronous message passing as the foundation of all the other traits. If your components in your system talk with asynchronous messages, they are really loosely coupled, and this also allows for the decoupling of using a component and failure handling. Okay, that was just a very quick overview about reactive, and let's see how we can go reactive with Akka and AngularJS. As a word of caution, I don't have too many slides. I have a lot of live demos. I hope you like code. We won't have enough time to really understand the code snippets I will show, but I hope you get the gist. And of course, if you have questions, please ask them anytime. We're going to build a little chat application, and it's named Reactive Flows. So here are the chat rooms. They are called flows, like Akka and AngularJS, for example. Here are the messages for the active, for the current flow. And here are, well, ways to enter new messages. Does that make sense? Sorry? Oh, that's interesting. Okay. Aha. This system is not really responsive. So here's the architecture. We're going to build a really resilient system until the end of this presentation, where we have a cluster, and here we see two nodes at the backend, both using Akka HTTP to provide a RESTful API and also to provide events via server sent events. Here, the browser frontend is AngularJS, and then we use some other Akka modules like distributed data, cluster sharding, and Akka persistence to make use of the cluster. In Akka, we are using actors, and this is the actor hierarchy for reactive flows. We have one root actor called Reactive Flows, which has only one main purpose, to create the so-called flow facade. And this is really our API, which we are interacting with. There's also a pub/sub mediator for publishing and subscribing events. And the flow facade manages flows, the chat rooms, okay? here are the messages we are going to send to the flow facade. You can look at this like an API, like calling methods, but it's not calling methods, it's asynchronous messages. Sorry. This sucks. Can we do something about that? No? Okay. Fantastic. So these are the messages we are going to send to Reactive Flows actor, like for example, get flows, and the actor will respond with a collection of flow descriptors containing the names and the labels of the flows. And of course, we will be able to add flows. Then we get a flow added if everything went fine. But if the flow already exists, we get a flow exists. The same for remove flow. And of course, we want to be able to get the messages for a particular flow. The flow, which is also an actor, has a simple protocol. It has a get messages command, and it will answer with a sequence of message objects. And of course, we can add messages. So we have an add message command with text, and the message added responds. Before we dive into the details of the backend, let's take a very brief look at the front end, which is implemented using AngularJS. So in AngularJS, we have HTML, templates, and as you can see here, this is not pure HTML. We have directives and expressions. In this example here, we iterate some variable called messages, which is defined in a controller, and MSG is just the iteration variable. We order by date, and we reverse the order. And then here, these are expressions which are used to fill in the blanks in the template. The controllers are just JavaScript, and what you can see here, or what you should take away from that, is that in the controllers, which is called home controller here, we have a variable holding the flows. This is just, yeah, sorry. Please tell me that earlier. That would be helpful. Thank you. And okay, here we have a variable for the flows, which is just dummy data here, and a variable for the messages. So with that in place, we can simply open our file. Oh, sorry, that was the wrong one. You couldn't see it? Okay, so that's it. That will be fun for a live demo. Oh my God. So that's just the static HTML with all the dummy data in it, as you have seen before on the slide, which you could see. Okay, let's dive into Akka HTTP, which is serving the HTTP interface for our backends. Akka HTTP is a fairly new module to the family of Akka modules. Has been released recently in version 2.4 of Akka, 2.4.2. And in order to provide an HTTP API, you have to invoke the bind and handle method of the HTTP extension, provide interface import, and a route. The route is a really interesting thing here. The route defines essentially a mapping from requests to responses. Okay, and there's a nice Scala DSL to do that, which you can hopefully see here. That's just a small example for the route method, which I have shown on the previous slide. Here we define assets and stop as two subroutes, and then we combine them. I think I will switch over to the IDE. As I promised you, HTTP service extends actor, open curly brace. Huh? So let's go up here where the route method is defined. And as you can see here, we define two subroutes called assets and stop. And here we just combine them using an OR operator. So these assets just React to get requests, and they serve it from the resource directory called web. So in our project, we have a source main resources web, which contains the index.html, for example, and other stuff. And here, stop is something you probably should not do in your production application. If you send a HTTP delete to the root path called path // the whole thing will just stop the HTTP service. So here we have an actor, it's called HTTP service, and once it gets the stop message, it will, as you can see here, stop itself, and then, well, everything goes down. It's just for the fun of it. So let me start it here. Switching windows. Oh, that works now. Excellent. Okay, if I go here, I can see my dummy page now, not from the file system, but from served by Akka HTTP. And if I use curl to send a delete to localhost, I think 8000, yeah, it stops the whole thing. As you can see here, it went down. No more working. Okay, so this is the very basics of Akka HTTP, of the routing. And of course, this is not yet enough. We need a little more to get the whole thing working as we expect. So let me move on to the next step in the solution where we provide a complete service, which is complete in the sense that it will provide a HTTP API for all the commands you can send to the flow facade. But there's still some things missing. I will show you in a moment. I'm starting it again, and if I go here now, let me see if it's already there. No, it's still compiling. Has somebody told you that the Scala compiler is not that fast? Of course, it's a very weak machine I have here, so it's not the fault of the compiler. Yes. Here we go. So if you go here, we can see a naked page now. Let's add some stuff. I think I have already something here. So this is curl just to add a flow. Oh, that's the wrong port. I'm sorry. 8000. Okay, cool. Now we added a flow. If we go back here, we cannot see it. But if we hit refresh, it's there. Okay, like 20 years ago, always hitting refresh. So the problem with our application is it's working, almost working, but we always have to hit refresh. So as you can see here, the backend is wired via HTTP, but we don't get any events from the server, which would be really nice. Huh? So this is the next step then. We are going to use service and events for that. Do you guys know service and events? It's okay, just a couple of you. So it's almost like WebSockets Lite. It's if you don't need a bidirectional channel, but only a unidirectional channel from the server to the client. Then it's a really nice way. So it's an official standard. It's supported by all the important browsers. Come on, under consideration. And the concept is really simple. It's all HTTP based, and the browser does get to some URL. In this case, it's called messages or message events or whatever. And the server will respond, but not close the response. Instead, it will keep it open and send messages. And those messages have a very simple format. They are text-based and new line-based. So you have these identifiers or headers like event and data. And there's also ID and retry. And the data is really important. That contains a payload, and the event is just like a designator. Is it an added or a removed or whatever kind of event? In the browser, we have the event source API. That's standard browser JavaScript API. We just need to connect to it. We can configure that event source using exponential back-off retries and stuff, but I think the defaults are not too bad. So this is all you need, message events as a path, and then add an event listener for, in this case, events of type added. And as you can see here, we just take whatever's there, the event data, parse it as JSON, and what happens here is if a message was added to a flow with the name of the current flow name, then we add this message. So that hopefully pushes the message to the browser. On the server, it's really easy to work with that. I will show you that code in the IDE. So as you can see here, the route has grown. We not only have assets and stop, we have flows, which I haven't shown you yet, but I can only do that briefly because of the time. So the flows starts with a path prefix of flows, and then if we have the rest of the path as one segment and then messages, we do get, or we react on get, and we react on post. So this would get the messages for a particular flow identified by that flow name, or that would just add a message. And for all these things, we interact with the flow facade. So we have our flow facade actor here, and we use the question mark operator to send a message, in this case the get messages command, or here the add message command to that flow facade. And then in this pattern match section, in this partial function, we deal with the response in an asynchronous way. So this is completely asynchronous and non-blocking. When it comes to the events, to SSE, all we have to do is register those endpoints, flow events and message events. And that's the code that is necessary to push events to the client using a library called Akka SSE, which is another Akka module, not part of the official library, might be merged one day. And here we have source, that's part of Akka Streams, which has been released together with Akka HTTP. So essentially what we do here is we define an actor as a source to push those service and events to the client. So each event that comes in is converted to a service and event using this function, and then more or less pushed to the client. I don't want to dive into the very details, but as you can see here, it's just a couple of lines of code. And if I start it again, we hopefully will see that it works like or as expected. So let me first show the naked page again and add one flow. And as you can see here, hooray, the flow is there. And if we add a message, it also pops up immediately. And it pops up immediately on any browser that is connected to the server. So hey, we're there. We have a fully working HTTP application, but it's not yet reactive in the sense of the Reactive Manifesto because it's neither scalable nor resilient. As you can see here, if I kill the server, it's gone. Okay, so we need to make it reactive. Let me check my time. Okay, I still have a little bit. That's good. So the first thing I want to introduce is distributed data. It's a module that deals with the question of replicating data without central coordination. Central coordination comes at a cost, so it would be nice if we can avoid it. And recent research has shown that there are certain data structures which allow for eventual consistency without any central coordination. And these are called conflict-free replicated data types. They're two flavors of those, but that's not too important. This module, Akka Distributed Data, offers various CRDTs, like counters, sets, and maps. It's important to understand that you cannot use arbitrary data types, like, for example, lists or whatever. They have to fulfill certain properties. Like, for example, in Akka Distributed Data, they need to have a monotonic merge function. For example, a set is perfect for that, because if you have two sets and here we add A and here we add A and then we merge, that doesn't hurt, right? Because you only can ever add an element once to a set. When we want to use Akka Distributed Data, we talk to an actor, which is provided by that module. It's called replicator. So we can send update messages to that actor. We can send get messages, and we can also register as a subscriber to changes. And on each node in the cluster, the replicator is running, and they know each other and disseminate the information via a gossip protocol. Well, you can actually even make sure that once you update, the replicator only acknowledges that update if you have directly written it to 2, 3, or even a quorum of other nodes, but by default you only write it to the local replicator and then it's disseminated via gossip. It all depends on a couple of fine-tuning and your consistency strategy. Okay, let me show you what that means. So we will start 2 nodes now and disseminate the information about the flows. If you look at the UI so far, okay, you cannot look at the, maybe here, no, here, okay. With 2 kinds of information in our system. One is just the names and labels of all the flows, which are kept in the flow facade so far. And then each flow itself is an actor which keeps the messages, which are shown here. What we are going to do now is we are going to move this information, which flows exist in the system, to distributed data. So it's available on any node in an eventually consistent fashion. So let's start a first node. And later we need to start a second node. I have some shortcuts for that. And if I want to create a new flow, I have to go to this 8001. Maybe I can show you in the meantime what has been changed here. So the flow facade actor earlier kept the information which flows exist in this map only. So we have the flows by name map, which just maps the flow by its label to a flow descriptor, and the descriptor just keeps the name and the label. And now we subscribe to the replicator. As you can see here, we send the subscribe message to this distributed data replicator, which means that we will get changed events from that replicator, and we just take those and update our map here. So we get all the updates from all the other nodes. So meanwhile, this is up and running. So let me go here. Hooray. Let me add a flow. Okay. Then let's start a second. Oh, that's a typo. Reactive flows, RF. Let's start a second node. Okay, up and running, looks good. Hooray, so what you can see here is we are on a second node, and we also have the Akka flow descriptor available. And I can now say I add another flow, like Angular or AngularJS on the second node, and it is available here and here immediately. So there should be a very, very slight delay because of the dissemination via the gossip protocol, but as you can see here on a local system with 2 nodes, that's pretty fast. So we're not yet there because we only distribute this information, which flows, essentially which names and labels exist in the system. So if we add something here, it doesn't work because the flows no longer know where to live, on which node, and it's more or less arbitrary whether they find it or not. So what we have to do now is the following. We need to use cluster sharding, which is another module that enables to partition actors across a cluster of Akka actor systems. So you almost get a virtual actor system which spans the whole cluster. In Akka cluster sharding, the shards manage a couple of actors, just like in database sharding, the databases manage a set of data. And the nice thing is that it adapts to the cluster topology. So that means if you add more nodes, existing actors will be repartitioned according to a strategy which is configurable. So by default, you get the least allocation strategy, which means if you have a new node which doesn't yet hold any of the actors to be sharded, existing actors will be reallocated to the fresh node. It's important to understand that this only works with actors that can be identified, and they are also usually called entities. Because if you want to speak or talk to such an actor, you no longer talk to it directly. You talk to the so-called shard region, which is another actor, part of this cluster sharding module. And the shard region knows where the actors which you want to talk to live. So for example, here we have actors A, B, and C. A and B are managed by this shard region. So if you want to talk to A or B, this will happen locally in your system. On the other hand, there is C on this other node. And if you want to talk to C, this shard region knows that this other shard region manages C and will forward the message to the other node. So this is a level of interaction which makes it completely transparent for you where those actors live in the cluster, which essentially gives you this illusion of a single actor system which spans the whole cluster. So the idea is to apply cluster sharding to our flows to make sure that we can have a lot of flows, chat rooms with a lot of messages, and make use of and distribute those flows equally in the cluster and make use of all the cluster resources. So if we start the system again, just a single system and maybe also the second before we add any flows and any messages. All right. Then let's add the Akka flow and the AngularJS flow. Let's see what happens here on the first node. Hooray, we have 2 flows. Looks good. Now let's add an Akka message here. As you can see, that works, and Angular, it also works. Great. Let's look at the other node, 8002. 8002 also has this information. And that's because, let me go back to this slide here. We have 2 nodes, and in our example, the first flow, which is called Akka, was created here. And the second flow, which was called AngularJS, was created over there because of the least allocation strategy. 1 actor here, 0 there, so the second was moved to the second node. Probably. We don't know because we don't have to know in this case. So we are almost there. We now have scalable system, which at least can scale up. But if something happens, or if we want to scale down, so for example, if we shut down this node here, we have a problem. Because what we have done now, what I have done now, is I have just killed the second node, and that probably was the home of the AngularJS flow. So the Akka flow is still there, as you can see, and the AngularJS flow, well, it's still there because it has been rebalanced. It has been recreated on the first node. But the problem is, it is in a fresh state, freshly initialized state without any messages. So we cannot really move actors across actor systems. They are not serializable. So what we do instead is, or what class sharding does instead is it creates a new actor, okay? So reallocating actors means creating new actors. So we have lost the state. Does that make sense? So we have to solve that final problem. And that's when Akka persistence enters the stage. Akka persistence is not a database library. It is to answer the question how actor state can be persisted and recovered. And it makes use of event sourcing. Have you heard about event sourcing? A couple of you. Okay. So in a nutshell, in event sourcing, you take a command, like, for example, persist something. You validate the command if it's okay to persist that entity, or maybe not because of some preconditions. And then you talk to the database, which is called journal in Akka persistence. And that journal is told to persist the event, and only once that has happened, it'll get back to you, to your persistent actor, and tell you, okay, I'm done. I have successfully persisted the event, and only then you apply this event to your local actor state. So once you restart your actor, all the events are replayed, and you end up in the same actor state again. Does that make sense? Great. And it's important to understand that we don't just persist all the commands, all the messages that arrive, because if they are not valid, we don't want to replay them and stuff like that. So we only want to persist and replay the valid events. Of course, there are features like snapshots to make that really work in scenarios where you have a lot of events persisted and a couple of details. And what's really nice about that is you can really do some time travels if you want to. So all of these things are possible with Akka persistence and event sourcing. So let me show you how that works. So the challenge for us is to change the flow actor and make it a persistent actor. Okay. So let me show you the flow. It looks like this now. Earlier it just extended actor, and now it extends persistent actor. So it has two methods that need to be implemented: receive command and receive recover. In the receive command, we still handle the command get messages like before, because that doesn't involve any persistence. That's just a read-only command, so to say. We just send the messages back to the sender. But once we get the add message command, we dive down to this method here, add message, where we invoke the persist method that is provided by this persistent actor trait. And the first argument to that persist method is an event, message added. So we create the event and tell Akka persistence to persist it. Once that has happened successfully, the persist method will invoke this callback as a function. So we get the event, the now successfully persisted event, back and apply to our state. And in order to apply it, we just invoke the receive recover, which applies the state changes. As you can see here, in a way that we just add the message to the list or sequence of stored messages. And then after that, we also do some side effects. It's important to distinguish between applying state changes and side effects, which is done here. So we publish the event. So we send the publish method to the distributed pub sub. We only want to do that once and not again on recovery, right? Because the event has already happened. So it's important to distinguish between this receive recover invocation and the other side effects. And that's it. So start that again. What's going on here? I'm renamed something. That's not a good idea. In the flow. No, I think it's a flow facade. Thank you. Okay, that looks better. So I'm going to start the two nodes again. And the first is already up, so I can add the Akka flow. And I can also now, the second is up, add the AngularJS flow. Look what's going on. No, 800 is not a good idea. 8,000. Okay. And as you can see here, we already have Akka rocks. Because the whole thing is, of course, Akka persistence is backed by a database. So in this case, I'm using Cassandra. There's a couple of plugins for the journal. You can either use some local databases or some distributed databases. I would say only distributed databases make sense in this distributed setting, and I think Cassandra and Kafka are the both production-ready plugins for Akka persistence I'm aware of. So it looks like this database has not been empty, but there has already been something in it. So that also looks good. So we have two flow messages in both flows now. And if we decide to move that down, and by the way, you can see now that Akka cluster is recognizing that because of a failure detector that the other node is no longer available, and with the settings I have defined here, it will automatically remove that unreachable node from the cluster, and that is the signal for cluster sharding to rebalance. And let's see what happens. So if we go to AngularJS, those messages are still there as before. Hooray, mission accomplished. So that was a very quick overview about creating reactive apps with Akka, using a couple of Akka modules, HTTP, distributed data, persistence, etc. And that's what I wanted to show you. And we still have time for a couple of questions, I think. Are there any questions? Come on. Yeah.
You showed us the changes you had to make when you introduced the Akka persistence. Do you have to make any changes to your entities in order to use cluster sharding?
So the question was whether one has to make changes to the entities, to the actors when you want to use cluster sharding. No, you don't have to do that. If you use cluster sharding and your actors don't have any state, you don't have to make them persistent actors. In many cases, though, you want to use those in combination. So usually if you use cluster sharding, at least some of your actors should become persistent actors. More questions?
Let's say if you have a considerable delay between the nodes or something, do you still have consistent ordering of the posts?
So the question was, if there's a delay in the network between the nodes, whether the posts have a consistent ordering. Do you mean the posts that go to the chat rooms?
Yeah. Those.
Yes, they have a well-defined order, because that's If I go back to cluster sharding, so these ABC could be just flows with those fancy names, ABC or Akka, AngularJS. So they only exist once, okay? In some location on some node. And any message you send there, or any message, blog post, the post message is kept there in the local storage, which is a sequence and has an order. So it really happens when those messages arrive, but they have a well-defined order. There was another question over there, right? Okay.
Yeah, generic question towards actor systems. So, is there any design advice? What do I design as actor and what not?
So the question was, which parts of the system should become actors and which should not be actors? Well, so the actor model is fairly old, and the guy who invented it, Carl Hewitt, once said, "One actors, no actors, they come in systems." So usually I would say a lot of things become actors. They are fairly low level. Well, it really depends. If you look at the architecture here, we have more high-level actors and a couple of low-level actors. Are you familiar with DDD, domain-driven design? Yeah. Okay, so the DDD community has great interest in Akka and also Akka persistence and these things. So it looks like it's common sense there that the aggregate roots are perfectly suited to be persistent actors. Okay. And then on the other hand, messages which are part of the protocol an actor speaks are of course not actors themselves. So typically you have actors, you have messages, and of course you need to implement stuff in your actors. So in my case, these were a couple of methods. Sometimes they don't have anything to do with actor lifecycle or something. Then you could move them to a normal class or object. So when I write Akka-based systems, I usually model a lot of the entities as actors and only, I would say, value objects not as actors, and of course functionality as normal methods somewhere. More questions? Okay, great. Then thanks. Enjoy the rest of the conference. If you want to check out the code, it's up on GitHub. And thanks for your attention.